Greetings everyone. Hope you are doing okay. Today we are going to present our Power System 2 project titled as Design of a Zonal UFLS Scheme in IEEE 39 bus network. We are group 3. Let's get started. Contingencies such as generator tripping, large load reconnection are common events in power system. After a contingency, power imbalance arises and frequency starts to fall. To arrest this fall, load shedding are done to restore the balance of power. Two types of load shedding are practiced in this arena. Firstly, conventional, secondly, zone-wise. In this project, we will apply both conventional and zonal UFLS scheme to restore the frequency and compare them based on parameters such as rate of change of frequency and frequency nadir. Along with this, we will also observe the effect of load frequency relief, which represents the change in load that occurs when power system frequency changes on both schemes. In zone-wise UFLS scheme, the load buses are ranked according to their strength and different amount of loads are cut off from different zones. This will help us keeping the important loads and also maintaining the bus voltages constant with the improved frequency response.
Here we can see the single line diagram of 39 bus system. Our system frequency is 50 Hz. There are 34 lines, 12 transformers, 10 generators and 19 load in the system. After performing the load analysis, we can see the output here. There is only one overloaded line, but it is not exceeding the emergency loading limit. So we can conclude that the system is stable and all the system variables are within the operational limit.
Then generator Z08 was tripped and 540 megawatt generation was lost. After performing frequency analysis, the attached graph was found. From the graph, we see that the frequency is falling after the contingency. The rate of change of frequency was 0.2 Hz per second. If the frequency is not restored within allowed value, the system will go to blackout. Now we apply a conventional UFLS scheme without zoning. We can see the scheme here. We have set three frequency threshold values at 49 Hz, 48.5 Hz and 48 Hz. Load shedding amount at 49 Hz is 15%, at 48.5 Hz it is 10%, and 48 Hz it is also 10%. From the output graph, we observe that the frequency excursion is stopped. Here, frequency nadir is 48.93779 Hz and rock-off is 0.1916 Hz per second, which is slight improvement from before.
Now, we will consider the effect of load frequency relief. In the swing equation, Pm is mechanical power, Pe is electrical power. Increasing LFR reduces Pe. As a result, contingency size reduces. So frequency nadir and rock-off improves, which implies better frequency response. In the table, value of frequency nadir and rock-off is given for different values of Kp. With the increase of Kp, rock-off improves. Although frequency nadir remains almost same, positive impact of LFR is visible here.
Ranking of buses. To rank the strength of the buses, we have to perform QV analysis. It involves continuously increasing reactive power until stability limit is reached. Reactive power margin is calculated from base MVR and minimum MVR. We have performed QV analysis for all load buses in PSSC. Here is the output. Higher the reactive power margin, the more strong the bus is. Here bus 12 is the weakest one and 16 is the strongest one. Next we have to develop a zoning scheme. Firstly, PQ buses are zoned according to reactive power margin ranking. Various reactive power margin thresholds are set to create 4 zones: very weak, weak, strong and very strong. Here the scheme of the PQ buses. Then PV buses are zoned according to geographically connected area and difference between the base MVAR and maximum MVR. Higher the reserve MVR, the more strong the generator bus is. Here the zonal scheme for the PV bus. And finally, the other buses are zoned based on the distance from generator buses. Higher the distance, the more weak the bus is. This is the zonal scheme, and the final zonal scheme is here. We have created 4 zones of very weak, weak, strong, and very strong, and the associated buses are here. Zonal UFLS scheme. We have applied a zonal UFLS scheme to arrest the fall of frequency. Here is our zonal UFLS scheme. Some of the characteristics of this scheme are: higher amount of load shedding are done on the weaker zones, and the amount decreases for the stronger zones. Load shedding is initiated first at very weak zone and then gradually at relatively stronger zone, and quick cut of load at weak zone.
Now in the following graph we see a comparison between the frequency response for conventional IEEE and zonal IEEE schemes. Here the blue one shows the frequency response for conventional IEEE and the orange curve is for the zonal IEEE. As you can see here, zonal IEEE gives us a lower rate of change of frequency compared to conventional IEEE and also offers us a significantly better native frequency. Now in the following chart we see a comparison with the different amounts of load shed for zonal IEEE and conventional IEEE schemes. For the zonal IEEE, larger amounts of load were shed initially for the zones with weaker buses, which reduces consecutively to the stronger buses. In the next chart, we see a comparison of the Brokoff and native frequencies for the conventional and zonal frequencies, zonal IEEE schemes. And we see that for the zonal IEEE schemes, we get much better rate of change of frequencies and native frequencies, which is desirable. Now we study the effect of different load frequency beliefs on a zonal IEEE schemes. We use KP values of 0, 1, 2 and 3% and observe the frequency response for each of them. We see here as the value of KP increases, we get a better Brokoff and native frequency values, the best one being for KP equal to 3%, which can be seen by the yellow curve. Finally, load shedding is not desirable at all to deal with power imbalances in the power system and should be used as a last resort. Using a zonal approach in load shedding helps us obtain better native frequencies and rate of change of frequencies so that we can restore the frequency to its nominal value faster. This method is very useful for our country where generation capacity cannot meet the demand of the users. That's all. Thank you.